Okay, so let's start slowly. I guess that some of you might have taken a course from me about when was it? This is spring 2021. I think in 419, right? Yeah, in 419, so almost 2 years ago, I taught a course in viscosity solutions. So some of you here might have been in the class and you have seen thorough discussions on viscosity solutions. For this class, I'm gonna take it briefly though, because it takes a while to actually give you a complete theory. And my point is that I'm gonna describe to you very, very brief but key points of viscosity solutions. And it turns out that that the viscosity solution gonna fit nicely with the Wickham solution. So everything fits together. That's the point. And uh, uh, if you have questions or if you want to discuss something, let me know um, before I start. Do let me know if you have any concerns or okay. Um, for further references, you can just read. I mean, chapter one of my book is probably good enough. Um, yeah, I mean there are lots of connections, but I'll walk you through. But I mean, my point is just to give you a bare minimum of what is needed because our focus is more on dynamics. So okay. Anyway, so I recall quickly the one example or two examples we did last time here. The two examples. The first one was that we have a normal Hamilton-Jacobi equations with kinetic energy and zero potential energy, and the initial data is a little bit weird. So it's concave and it's sort of going downward like that. So in such a case, you would have that. In this case, you would have that g prime of x equals to 1 for x less than 0 and minus 1 for x positive. So therefore, you would find that the slopes of the backward characteristic starting from something less than 0 is going to be having slope 1, right? Because that's exactly the slope here, right? The slope is g prime of x, okay? Um, and then if you were to start from the right for x greater than 0, you would have slope minus 1 coming exactly from z prime. So you see that characteristic run into each other in a quite symmetric way here, which is fine. I mean, we are not worried about that. The only issue is that you see that for x very tiny, close to 0, x minus x, you see that characteristic run into each other, so characteristic from x and minus x run into each other at 0x in an amount of x time, okay? And you see that that would mean that if you take x tiny, right, the time slide gonna get smaller and smaller, and basically that means that we can say that characteristic cross each other instantly for any time. So this is bad because it means that method of characteristic doesn't even give local solution, right? Don't even doesn't local in time solution, right? You cannot find a small time interval in which characteristic don't cross. So I mean, we have to be careful when we say local in time. We need to impose conditions appropriately. Okay. The other case that, of course, I can revisit the first example, but I'll revisit. I'll introduce you another example that is in a similar flavor later on. Um, uh, and maybe my question for you in this case that check to find what's the viscosity solution in this case later. Viscosity. Okay. The other example that I want to recall quickly is it's the same example. I don't know why I deleted one half here. Um, yeah, it doesn't matter. I should kept one half, but fine. I mean, I deleted sorry, one half. And I see that this is one of the solution, and this should be the physically correct one because we start from zero. We have nothing, right? But however, we will also be able to point out another solutions that is fine, uh, except at the three rays here, right? And then it looks pretty nice, you know. It's crap. I don't know how to draw its picture, but basically in these two corners is zero, right? Stay zero, and then somehow it dips down, right? I mean, it's sort of like it gets down to minus t, so there's a ray that's sort of going to minus infinity here. This one is going to minus infinity, and then you know it's sort of two wedges coming down, right? You know, you have the two wedges stay here, and then two wedges sort of like dipping down. And again, I really don't know how to draw that 3D picture. You know, I'm drawing something ridiculous because so those are the wedges uh, sort of going down. Yeah, this is a weird picture because you know I'm doing nothing. So one of the thing I would like you to imagine is that later on we're gonna touch upon this is that if you take this right, and then you would see that your solution does something like, you know, it would go up like that, right? You know, locally it would go up like that. Okay, so it has the two wing, you know, sort of watching down at the ray 0t. Okay, that's sort of the picture, roughly speaking. That let's keep this in our mind later on. Okay, so or I can say that this is sort of a minimum mean where the function takes a minimum value, right? Okay, fine. Um, so let's keep those picture in our mind. I'll use that later. Okay, so now let's a modern way. This started from the 60s and then up to the 90s. There's a well-postness theory. This is based upon the work of Crandall-Lyons, of course. And earlier there was already a work by Evans defining viscosity solution. So I'll go quick here. The idea is basically people borrow it from fluid mechanics or other fields. From the 60s, from the work of Fleming's, 60, there was a work of Fleming, and also there was a work by Khrushchev for conservation laws that people really try to, you know, use the ideas that, you know, if you go from fluids, so they have the viscosity, right? There's a certain sort of like viscous things that connect the material in the fluid, and then you try to pass the limit, letting the viscosity going to zero. So that's essentially the idea from Navier-Stokes to Euler, right? But from Navier-Stokes to Euler is harder, much harder, because it's a system of three equations. This is just a single equation, so it's simpler. But the idea is really beautiful. Is that people try, you know, you in the PD way is totally different from dynamical system way, right? Dynamical system, we were looking at parts and stuff like that. For PD, we started with, you know, an equation, and we try to look at the vanishing viscosity limit. So essentially for h epsilon greater than zero, you introduce the smoothing terms, epsilon Laplacian of u epsilon, and you look at the equation, right? You know, again, I deleted any irrelevant parameters here. I'm just looking at the simplest equation. equals to epsilon Laplacian of u epsilon, right? In Rn cross 0 infinity. So again, this is a smoothing effect. And if you look at what I'm highlighting here, um, the two terms I'm highlighting essentially is the heat equation, right? And then you can treat the other terms here, h of d epsilon as the perturbation term, as a first order term, right? Again, for fixed epsilon greater than 0, this is essentially a quasi-linear heat equation. You have a heat equation and then you have a perturbation term of lower order term, first order, okay? That's the way people look at that. And then you have the initial data is just this one. We call this one hg epsilon. Okay, again, yeah, so let me say for epsilon greater than 0, u epsilon t minus epsilon Laplacian of u epsilon is the most important term. And h of du epsilon can be treated as a perturbation term. Okay, and you can evoke any kind of regularity theory or any kind of there are different ways to prove the existence of solution to this thing. You can prove a priori estimates, and you can do fixed point theorems, or sometimes that, you know, for this kind of equation you can also write directly. You can so either you have a priori estimates, and then you use fixed point theorem to have the existence, and then uniqueness, because uniqueness is clear because you have a heat equation. You can just use the maximum principle, or sometimes you can do directly. This sometimes people do it. You know, you can think of the equation as given v, let's say Lipschitz, whatever, and then you look at the PDE, like u t minus epsilon Laplacian of u equals to h of dv, and this can be treated as f, right? F of x t. H of dv is f of x t. Then you can use the representation formula for u. So you write down formula for u, right? We do have a formula for u here, and by Duhamel formula, Duhamel principle, you write out the formula and you run the fixed point theorem directly, because what you're doing here is that you have a map v maps to phi of v, which is u, and then you prove that this map and show that phi has a fixed point. Okay, so I mean, I'm telling you that this PD is pretty well known. Oops. That under certain assumptions that H is smooth enough and G is smooth enough, and certain bounds, you have that the equation Hg epsilon is a heat equation type. So it has a unique smooth solution, smooth up to the order of H. So if H is Ck, U epsilon is Ck or Ck plus 2, whatever, doesn't matter. And moreover, what is important is that it has the maximum principle, right? So hiddenly there, when you add the epsilon Laplacian and you add this term, you have that, you know, the structure here has the maximum principle, right? Again, when epsilon is positive, people can treat this one as a perturbation term, and it has a maximum principle. And then the questions that people in PD ask is that what happened as epsilon goes to 0? Do we converge to a unique limit? Does it solve our Hamilton-Jacobi equation. Okay, so that's sort of the question. What is really interesting is that you see that when epsilon is positive, we are treating h of du epsilon as a perturbation term, essentially. But when epsilon goes to zero, there's no second order term. Then h of d epsilon plays the crucial role, right? So I mean that's sort of the very interesting point. And it turns out that, again, I'm skipping the details. Under certain conditions, you can show that U epsilon is uniformly Lipschitz uh, and bounded, locally bounded. And you can find that there exists a subsequent epsilon k converging to zero, such that you have U epsilon k converge to U locally uniformly in Rn. Okay, so so we don't have yet that it converges to anything meaningful, but we know that there is a subsequent epsilon k going to zero by just azilascally, such that we have U epsilon k converge to U locally uniformly on Rn cross zero infinity. Okay, so that's the point. So I only have the the uniform conversion, so we don't have conversion of du epsilon to du in a strong sense, right? In a strong sense. I mean, when you say that du epsilon is bounded, you can say that it converges to du in the weak star sense, in L infinity, but it doesn't converge in a strong sense. And if you look into the equation, right, I have u epsilon t plus okay plus h of du epsilon k equals to epsilon Laplacian of u f k. Okay, so I let epsilon k goes to infinity to zero. K goes to infinity. Um, this one only converges to ut in the weak sense, right? Inside here only converges to du in the weak sense, in certain weak sense. I have no ideas about the Laplacian. This one doesn't converge to anything. I don't know. And h is moreover the function h is nonlinear, right? So a nonlinear function acting on something that is weakly convergent to something. I have no ideas whether uh, h of du epsilon k gonna converge to h of du or not. So there are all the very difficult points in passing to the limit, right? And this is why, also that it's really hard to go from Navier-Stokes to Euler. I mean, it's much harder, but I mean, um, and there's a nonlinearity in Navier-Stokes and Euler. Same here, h of d epsilon acting as a nonlinearity, and we can't just pass the limit freely. So this is a big issue, and this is why that although the Hamilton-Jacobi equation was known from Hamilton-Jacobi and also from Lagrange time in the 18th, 19th century, um, I mean, roughly 1820, roughly speaking, there, but it could have been written down earlier. Um, but it took us only until 1980s to have a good rigorous theory to define solutions. Okay, so that's something, like nearly 200 years, right? So the key points now is sort of like to define which solution by based on maximum principle. Okay, so this is a very smart way. I mean, the definition we are using here is due to Evans, and he said that this is based upon something called Minty trick. Minty. So what we are doing is that we are not going to deal with those difficulty, the nonlinearity here, and we have no idea about the conversion of the Laplacian here. We're gonna try to pass the difficulty to the test functions, and it's really beautiful. So here's how it goes. So I'm just gonna recall the max principle with you, and then you see the key points. um I'll explain why do we need to use test functions. But so if u epsilon minus phi has a strict maximum at ys, okay, so we have u epsilon is our for epsilon fixed is our solution to the PD, and it's smooth, right? And phi is a test function. So geometrically, when I'm saying that u epsilon minus phi has a maximum at ys, then geometrically you can think of the fact that u epsilon is being touched from above by phi at the point ys, uh, because at the point ys, then u epsilon minus phi equals 0, and at other places it's less than 0. So that's a geometric picture to think about a function being touched from above and below. And this is a very, very important viewpoint for nonlinear PD. I mean, from this school of thought, so from Caffarelli's school of thought, it's really important. uh, so um so that's that. So I'm having a smooth test function phi popping out from nowhere. I'm touching it, touching the functions from above or below at certain points of testing, and assuming that ys is a maximum point, right? Then clearly, first, by using the maximum principle, you can see that the gradient equals to 0, right? So the gradient equals to 0, and the Hessian is less than equal to 0 at that point, right? uh Hold on, yeah, I think there was a mistake there, a typo there. So you see that the gradients are 0, so that means that the gradient of u equals to the gradient of phi. I mean, I'm saying the gradient uh in x and also the time derivative, they are equals. And the Hessian or the Laplacian, I can compare them, right? So I would have Laplacian of u epsilon at ys is going to be less than equals to Laplacian of phi at ys. Okay, yeah. So this is great. You see that this is just a very, very simple uh, maximum principle trick, right? But what is really important is this box I'm putting here. I am successful in transferring all the derivatives of u to phi, or u epsilon to phi. Okay, so the trick is that u epsilon is smooth, but u is not, right? Um, However, if I'm successfully transferring all the derivatives to phi, okay, then I'm good, because I have been able to switch all the dangerous things about differentiating things to a test function phi. Okay, so what is really beautiful is the fact that based on that, I have been able um, like in these conclusions that I have phi ys plus h of d phi ys is less than or equals to epsilon Laplacian of phi ys. In that, I have been able to pass all the derivatives to phi. Okay, so that's exactly the so-called Minty trick, or exactly the amazing idea of sort of like so this is sometimes called L infinity integration by parts. I cannot do integration by part here because h is nonlinear, but in a way I'm still trying to find a way to kick the derivatives from the solutions to the test functions. And I'm fine with the test functions because the test function is assumed to be smooth. Okay, so that's the key idea. Now we are going to use that to define viscosity solution. All right, so the geometric picture is this. So I have, u is this one, and u epsilon k is approximately equals to u, right? So u epsilon k is approximately equals to u. So you can imagine that u is certain function and u epsilon k is sort of oscillatory, or is sort of like approximating u. Now I'm still using a test function phi touching u from above because I want to define solution for u, right? So what I'm doing is that I'm assuming that u minus phi has a strict maximum at x naught t naught. Okay. Yeah, maybe let me draw a picture for you guys here before coming to the definition. I mean, once we understand that it's easy. So u, in principle, you have seen in all the things we have discussed that u might not be smooth in all the examples, and also in Wickham theory, u is at most Lipschitz. Okay, so it can have corners from above and below. So roughly speaking, this is sort of a picture of that. Now I have phi touches u from above at x naught t naught. So this means that u minus phi has a strict max at x naught t naught. Okay, so there are two ways for you to visualize this picture. The first way to visualize this picture is to look at u and phi separately like this, and geometrically that means that phi touches u from above at that point. Or you can also view the whole graph of u minus phi. Okay, if you look at the whole graph of u minus phi, it would be, roughly speaking, this. So this is u minus phi, and it has the, oh no, it's wrong. I'm sorry. So this would be the graph of u minus phi, right? X naught t naught. So if you look at the graph of u minus phi, then it has a strict maximum at one point, x naught t naught. Okay, so there are two ways, two different ways to visualize the picture. Now, I know that u epsilon k is near u, right? So u epsilon k is something like this. U epsilon k. Okay, so u epsilon k is quite close to u. Okay, and clearly that you see that if u epsilon k is quite close to u, then a point that we can deduce is that u epsilon k minus phi has a max at xk tk, and roughly speaking xk tk, I mean bypassing to a subsequence or something like that, or you don't need in some cases. Xk tk converges to x0 t0 at k is equal to infinity. Okay, so that's a way to view it. So if you feel that this picture is not clear, then you can look at the picture below here. So I have the graph of u minus phi. Now let's have a look at the graph of u epsilon k minus phi. Okay, so you see that u epsilon k minus phi is also close to u minus phi, right? They're quite close to each other. So I mean, what it means that you can think of, you have a sort of like u minus phi is sort of a height of a certain mountain, right? And x naught t naught is the top of the mountain, and you are trying to take certain small perturbations of the mountain. You take a shower and you remove the soil from one place to the other a little bit. So basically it could be that u epsilon k minus phi is sort of being perturbed a little bit, right? So if you move a little bit of the soil from the peak to some other places nearby, then yeah, I mean this point would be xk tk, but it should be close to x naught t naught, right? I mean, that can be written in the epsilon delta term very very easily. So that's a geometric picture I want to explain to you. Once you see this picture, you see it very clearly what we are doing. So what we are doing is that we have u minus v has a strict mark at x naught t naught, and because u epsilon k converges to u locally uniformly, we can say that u epsilon k minus v has a local max at a nearby point. But it's a little bit, the pitch is still going to be a nearby places, and xk tk converges to x0 t0 as k goes to infinity. All right, now we are using the maximum principle by the above analysis, right? At the maximum point, we have uh, phi t plus h of d phi, okay, is less than equals to epsilon k phi xk tk, right? It's the maximum principle. You see that we have been able to transfer all derivatives to test function phi, right? It's really amazing that we just transfer every derivative to the test function phi. Okay, it's remarkable. And the test function phi is fixed, it's chosen from the first place, and then we now we let k goes to infinity, right? You have xk tk converges to x naught t naught. So clearly that the first term converges to phi t of x naught t naught. The second term converges to h of d phi x naught t naught. And the last term here, again, phi is our smooth test function, fixed, and epsilon k converges to 0, right? So therefore, the right-hand side converges to 0. Okay, that's amazing, right? Because when I pass to the test function, I know the conversion. But if you look at the right-hand side, right panel here, if I'm using epsilon k, Laplacian of uk, I don't know anything about what happens if k goes to 0, right? I mean, it's bounded. That's what I know, but I don't know whether it converges to 0 or not, because u epsilon k can be really fluctuates, right? It's smooth, but it Hessian can be converging to infinity faster than 1 over epsilon k. Oh, I mean, I take it back. I mean, of that's rate, but it's not slower, so that thing doesn't converge to 0. Okay, and what is also remarkable is that you see that our equation was involving u, right? So let me write down here. So our Hamilton-Jacobi equation originally is ut plus h of du equals to 0. But because u is only Lipschitz, I don't know how to make sense of u at the non-differentiable point. So how to make sense of this at non-differentiable points, right? That I have no idea. But for example, this is u at non-differential point x naught t naught here. I don't know how to make sense of it, but if I'm touching it from above by a function phi, then the requirement would be that if this is the case, I would require that phi t at x naught t naught plus h of d phi at x naught t naught got to be less than or equal to 0. Okay, so this is an additional requirement at points that ut and du is not defined. But however, you see that I'm replacing ut and du by phi t and d phi, and phi is smooth, so that makes total sense. So that's really remarkable. Okay, so this is the first point of this is the so-called sub-solution property, which I wrote it here, right? Um, so the first part is the sub-solution property, that if it has a strict max here, then I would have is less than or equal to 0. Okay. And then there is a super solution property that if it has a strict means, then I have the other side at inequality. And in other words, that the second point is that uh, if you have this is your U, and if you can touch it from below by C at the point x1, t1, then you would have the ct x1, t1 plus h of dc x1, t1 greater or equal to 0. Okay, so those are the definitions. So I would say that let me make this remark and then we go to the example and we are done. So the remark I want to make is that viscosity solutions put additional requirement on non-differentiable points. Of U. Okay. Right. So let me stop for questions or discussions before I move on to the final part of the lecture. Questions, concerns? By the way, for those of you who haven't taken viscosity solution, is it quick or is it okay? I mean, I know that some of you have taken it, but I mean, of course, it was 2 years ago, nearly 2 years ago. Okay, good. Yeah, cool. So I mean, this is also another important point of philosophy that what it says is that like uh, uh, you look back at the examples, you see that you can design like this example, right? You can design many almost everywhere solutions though. So if you use that sort of like notions of just almost everywhere solution, you need to have many solutions. So therefore an important philosophical point of PD or mathematics in general is that if you want to have verbousness, if you want to restrict your attention to only one supposedly physically correct solution, then what you need to do is that you would need to impose more conditions, right? You would need to be a bit more restrictive in such a way that you select one only. And this is exactly what it means here, right? We are putting more conditions to make it more restrictive, right? So that we only select one solution out of it. And sometimes it's not that clear. I mean, sometimes that you can come up with nice definition of solution and stuff like that, but sometimes we are just not lucky. um, for example, my colleague Misha Feldman is a top world expert in conservation laws uh, for uh, for certain settings like single equations in one dimensions or system of equations in one dimensions. You can also do vanishing viscosity. That started from the work of Khrushchev, and for system it's really hard. There was a recent work by uh, um, uh, yeah, I forgot their names now. So by the Italian group Brescians and one more, just 10 years ago, that you can do vanishing viscosities. But in general, for a general system of conservation law in multi-dimensions, up to now, people come up with various different, Bressan and Bianchini, exactly, thank you. Yeah, so that's a remarkable paper in the annals more than 10 years ago. And Bianchini was a student of Bressan, and and but for general system of conservation laws in multi dimensions, you cannot so far come up with a good definitions of solutions. People come up with various different definitions, but for every single definition, you don't have well purposedness so far. There's counterexamples. There are things that make things go wrong. So sometimes you need luck. And in this case, we are lucky. In this case, we are lucky because this one gives exactly um, the correct definition. Okay, so we are lucky. So let's go back to the examples. And try to do it. By the way, I wouldn't have time to prove well purposedness for viscosity solution. I will just assume it. You guys can check my book chapter 1. Just everything about well purposedness, but you know, for for our time, I will try to go through this quickly and go to the very important points about large time behavior, combinations of dynamic and PD to tell you that. Okay. Um, All right, so let's come back to the examples we have earlier. This was the equation that we had. It was ut plus ux square equals to 0. Okay, and we want to show now that the functions here, that is not C1 at the 3 rays. And we're going to show that W is not a viscosity solution. Okay, so W is not a viscosity solution. Yeah, and you can see that clearly we have checked at the 4 regions inside in which W is smooth, right? I mean, then everything satisfied. What we need to rate only are the 3 rays in which W is not differentiable. And remember, there was a point I was telling you earlier, that if I look into this ray, the time right, and then the graph would sort of essentially be the 2 wedges going down. So it takes the minimum at the 0t, right, at the time right. And we are now going to use that um, to exactly prove the point. So I'm considering the function c of t to be exactly cxt to be exactly minus t. Okay, so the function is exactly that, right? And it's touching W from below at any point, right? Again, you can say that I'm cheating a little bit here. It's not a strict maximum, but that can be fixed. A minimum doesn't matter. So what I have is that W minus C has a minimum point at 0t, right? Because remember that our functions is sort of like going down like that. It's having a wedge down here, right? And the value down here is nothing but just minus t, right? You can take the value uh, x minus t or minus x minus t when x is 0 is exactly minus t. So W minus c essentially have every point on the time ray is a minimum point. Again, it's not a strict minimum, but that can be fixed easily. Um, so we say that W minus C has a minimum point, and let's check it out, right? If, looking at the second situation here on the right panel, if it touches from below, then it should have CT plus H of DC greater than equals to 0, right? But now let's check it. At the point of touching, let's compute CT plus DC square. CT is minus 1, right? DC is 0. There's no X dependent. So therefore, I have minus 1, and this is less than 0. And this doesn't satisfy the super solution test, right? It's not greater than 0. So therefore, we have the contradictions, and W is not a viscosity solution. So again, amazingly, in this case, again, we are lucky that this definition is amazing. It captures the only unique solution, and it's called the viscosity solution. Um, and moreover, you're gonna see that it fits really well with dynamics. It fits well with optimal control and everything, with differential games. So I mean, this definition turns out to be the correct one, to be the one. Okay, good. So let me finish now by this cute example. Again, this example is the one that people have been taken always. um, in any kind of textbook, including mine, that people take this example, that you have the slope is 1, and then at 2 entrance point is 0. And by the way, this is an Eikenhoff equation, although that is very simple, but it's actually a very, very important example in geometric optics. Um, so your graph can be anything, having segments of slope plus minus 1, right? Um, and the question is that what's going to be which one is going to be a viscosity solution. So let me do it just quickly. If you want to entertain yourself, remember that I asked you this question here, right? In this first example, the question I asked you would that what would be a viscosity solution, and check it out, So when you have the characteristic crossing each other instantaneously, then what's going to be the viscosity solution? It's quite evidently clear here by the hint of the characteristics, but why don't you check it out if you are curious? For me, let me finish the lecture by this example. So let's take a look at this kind of functions, right? So these functions, let's say this is v, then I have v prime of x is always plus or minus 1, except at the two corners here, right? At those two corners, then it's not differentiable, and I have to check it carefully. Now again, let's check the corner from below, right? So check the corner from below. The corner from below here, you can essentially touch it from below by any kind of smooth functions like this, right? So let's say this point is z. You can touch it from any smooth functions. So c, right? It's gonna touches v from below at z. And in fact, you can choose it so that c prime of z take any value between -1 and 1, right? Just the slope, right? The slope is changing from -1 to 1. So, and you can choose it to be anything, right? So in particular, you just choose c prime of z to be 0, I mean, whatever, right? And then um, the super solution test tell me that I should have c prime of z -1 should be greater than equals to 0, right? That's what I need, right? But clearly this is wrong because this one is -1. This is just contradiction. So therefore, any corner from below is invalid, okay? So the conclusion is that any corner from below is invalid. Okay, so this allows you to see that you cannot have a graph that has a corner from below. I'm not checking the corner from above. I just leave it for you for fun. Then you can see that then your unique viscosity solution is going to be this one. So this is a unique viscosity solution. Okay. And that's amazing. And for those of you who have been working on this, let me give you this sort of like a point in the dictionary, is that if your Hamiltonian is convex, then in general, okay, you have to check me on this, because there are certain cases that it could allow corner from above, but in general, the unique viscosity solution doesn't have corners from below and only corners from above. Okay? So it's a very important dictionary point. But I mean, it's evidently clear from this proof, because if you have a corner from below, you can touch it from below and of any function of any slopes, and you can make the slope to be small so that your super solution fails. Okay. Yeah, I'm going a little bit quick today, I guess. I mean, normally I would have focused a bit more on examples and talk more about details. But I hope that you are with me on the touching from above and below, and you can just have two more further criteria, right? Touching from above, you have less than equals to. Touching from below, you have greater than equals to. And that's it. We are good to go. And this fits totally well with CAM solutions. Questions, concerns?
So I have a simple question. So sometimes when people write the Hampton-Job equation, they write a negative ut instead of ut. Is that kind of like a backward interpretation? Can you comment something on that? Like,
Yeah, if you write negative ut, then it's a backward equation. You
okay,
put the terminal data. Yeah.
uh,
I mean, what's your point?
was there any kind of like benefit for writing so, or just
Um,
to emphasize the interpretation?
so I mean, okay, yeah. So that's a good point. So basically, when you write out backward Hamilton-Jacobi equations, this is often in the optimal control community that you would write out your equation like minus ut plus h of x du equals to 0 in Rn cross 0 t uxt equals to g of x. So this is a backward equations, and to make it back to the forward equation, you just so from backward to forward, you just do change a variable. Let phi xt equals to maybe w. Mm, equals to u of x t minus t, then w. So surely the forward equations, right, up to t plus h of x dw equals to 0, and w x0 equals to g of x. Okay, so that's the backward back to forward. And now let's say that why in the optimal control community, why do they like to write out the backward equation? um, the reason is because of interpretations only. So this is time t equals to t. um, uh, in optimal control, right? I mean, normally people would talk about the terminal time problem, not the initial time problem. You start from some time and you finish your duty at time t. That's all. So you go from here to here. So this is the finish time, right? Like your workload shift is like 8 hours. That's why they prefer the terminal time problem. So this is terminal. That's all. I mean, there's nothing more than that. And people said that, okay, for them, that makes more sense. But I mean, to me, it's the same. So you would have the definition of the solution uxt. By the optimal control formula is going to be infimum of all curves, gamma t starting from x. So if you start, this one is xt, and you would have gamma t starting from x, and you minimize the cost from t to big T, L of gamma dot SDS. So you pay the running cost and then the terminal cost, G of gamma T. So this is a terminal cost. So it's just in terms of terminology, right? The terminal cost and the terminal time sounds more natural. That's why people prefer that. But I mean, nothing different. Okay.
Thank you. Yeah.
Yeah. Yeah. Again. Yeah. But it's true. People in optimal control really prefer the terminal time problem. Again, I mean, to me, I prefer both. I mean, at the end of the day, once you get to, I mean, the more you do and the deeper you get to, my advice is that, I mean, I when was a grad student, I was thinking like I would only do these directions, and then there are so many viewpoints, I'm just gonna ignore them. And I realized that when I finished my PhD, starting the first month of my postdoc, I was like, oh, that's wrong. I should know every single point. I should, actually have all the different views of the problems and see everything through. And you know right, so thank you all and see you on Wednesday. Bye for now.